Hello everyone, I'd like to remind you that you should try these problems first and then watch these solutions. But here's the story. This next problem's interesting. So there's a point between the Earth, which I have drawn here with a big squiggle, and the Moon, where the gravitational pulls are going to be equal. It's going to be much closer to the Moon because the Moon can't pull as far. But there's a point where you can sit between the two objects and the gravitational pulls, one going this way, one going this way, will cancel out. And so that's the heart of this problem. They want us to figure out, okay, how far from the center of the Earth, which we'll call R1, is this point where the forces are going to be equal? So let's take a look at this. We want the gravitational force, okay, from the Earth to be equal to the gravitational force from the Moon. And we should be able to figure out the location using this equation. Now, the thing they gave us in the problem was that the mass of the Earth is 81 times the mass from the Moon, which this is what we're going to do to represent that. We're going to call the mass of the Moon M, okay? Well, actually, we'll call it big M, because it's pretty big. And then we'll make mass of Earth equal to 81 times big M. So I know I wrote 18 up here, but I meant 81. So 81 M. So the Moon is M, the Earth is 81 M. So let's use this equation. So the big gravitational equation is G, big M, little m, over R squared. And that should be equal to the same for the Moon. Now we gotta personalize this. Let's look at the diagram again. Big Earth, little Earth, spot where gravity is equal. It's going to be closer to the Moon. We'll call that R2. And we will try to be solving for R1, the distance from the center of the Earth to that point. So this one for the Earth will be R1. This one for the Moon will be R2. Now, the only thing different is that I needed to add in the 81 times for the Earth. So 81m is going to be there. Now, we have these two equations set up and personalized. Now we can start canceling stuff. And if we are lucky, which we are, all things on the top cancel out. If I divided both sides by G, they'd go away. Divided both sides by M, divided both sides by little m, that all goes away. And so what we're left with is 81 over R1 squared is equal to 1 over R2 squared, which is great. All right, so let's solve for R1. We'll cross multiply. And so what we get is 81 R2 squared is equal to R1 squared. All right, we're getting somewhere. Let's find the square root of both sides because everything is squared. 81 square rooted is just 9. So 9R2 is equal to R1. So that tells us that R1 is going to be 9 times longer than R2, which makes sense to me. All right, now the problem here is that R2 is something we don't really know. We don't really know that distance. And so what we're going to do, do I need to find the distance? Oh, no, we could use this to get the answer. So the options are 8/9 the way to the Moon, 9/10 the way to the Moon, and 3/4 or 80 over 81 the way to the Moon. Once we have this set up, we realize that R2 is 9 times smaller than R1, which means this is 9 times bigger, which means R1 is 9 consecutive equal pieces, and R2 is just one of those pieces. So that's 10 pieces total, and R1 is 9 of those 10 pieces. So that means that it's 9/10 the way to the Moon. That's option B. I thought they were looking for an actual number. I didn't read the question first. Never do that. All right, the torque caused by the force applied at a distance r from the axis of rotation is given by torque is equal to RF sine of theta, where theta is the angle between R and F. Okay? If the magnitudes R and F remain the same, what other angle theta would produce the same torque as was produced by angle theta if theta was less than 90 degrees? This is a silly question, all right? So think about this. If you had an object to rotate, say I had a pole attached to a point of rotation here, and it could rotate like this, or it could rotate like this, it could rotate in a circle around this point. Now, if I apply a torque like this, that is 90 degrees from my radius line, then I provide the maximum torque, which is why we use sine of theta to represent torque. Because if this is my maximum torque, sine of 90 degrees is equal to 1. Now, if we applied a force to the same object, just like this, going this way, just pulling on it, well, that's not going to get it to spin at all, which is why this angle of 180 degrees doesn't work at all. So sine of 180 degrees doesn't give us any torque. You get sine of 80 degrees, 180 degrees equals 0. So they're saying, okay, what if we had torque not at 90 degrees and not at 180 degrees? What if we had it at like this angle? Say this was like 45 degrees. They don't give us an actual angle, but say it was like this, okay? Now, this one is going to provide a torque, but it's not going to be the maximum torque. Sine of 45 gives us 0.707, which means it'd be like 70.7% of what that force could actually apply as torque, all right? And they're like, okay, if 45 degrees produces some torque, then what other angle, other than 45, will produce the same torque as was produced by that angle if it was less than 90 degrees? So, what other angle will produce the same amount, that 70.7%? So, let's look at this. What if we just had 45 degrees in the other direction? Okay, now that should provide the same torque, but the angle would be different, because if this is 45 degrees, this is not 45 degrees. This is 180 degrees minus 45 degrees, because the whole thing all the way to the back line would be 180, but we took away that 45 degrees there. So this would be the angle that would produce the same number, 180 minus 45 degrees. So they gave us an answer here where it's like the new angle would be equal to 180 minus theta, okay? So let's see if that works in general. What if we had one that wasn't 45? What if we had it was 20? So a 20 degree angle. Would that produce the same torque as 180 minus 20? What would that be? So 180 minus 20 would be 160. Sine of 160 degrees, that gives me 34% of my torque. Let's take a look at 20 degrees. So sine of 20 gives me that 34%. So it looks like we found our answer here, where if you take 180 and subtract theta, the angle you started with, you're going to end up with a equally capable force of applying torque. So you want to figure out these pairs that push in the correct direction an equal amount, but have the same angle on like opposite sides. 180 minus the original 80. All right. A 800 Newton billboard worker stands on a 4-meter scaffold weighing 500 newtons. So this is what it looks like. Scaffold, 4 meters long, and the whole thing weighs 500 newtons. Supported by vertical ropes at each end. Boom, boom, vertical ropes at each end. How far would the worker stand from one of the supporting ropes to produce a tension of 550 newtons in that rope? So these ropes are going to be doing different work depending on where this guy stands. So an 800 Newton billboard worker. So basically the two tensions have to keep that guy balanced. And I feel like this is one where I'd like to go to a clean piece of paper. So first, watch this. Look at the scaffold by itself, and let's figure out what the tensions are in that rope. So without the guy, we've got a 500 Newton weight. and that's being applied straight down from the center of mass in the center of the scaffold. I drew it a little too long. It should be, the ropes should be stationed at both ends, and the force of gravity should be directly down in the middle. Now, let's figure out the torques on this, talking about the axis of rotation being here. So this thing isn't rotating, so the net torque should equal 0. But it should be equal to T1, which I'll call the force on the left, T2, the torques from T1, the torques from T2, going up, and the torque from the force of gravity. Okay, now torque, all of these are acting at 90 degrees, so I don't need to worry about sine of theta right now. So this is F, so torque is equal to force times radius, and so the force for T1 times the radius. Well, the radius, if this whole thing is 4 meters, this would be a 2 meter radius, right? 2 meters, like that. So T1 times 2 meters, that's trying to get it to rotate this way. Now, force of gravity is great, but it doesn't have a radius. It's located directly at the center of rotation. So that would be multiplied by 0. And then you would subtract T2 because it's trying to rotate it in the other direction. Think about it. If it's a circle, T1 wants it to spin this way, and T2 wants it to spin this way. So they're going to be in opposite directions to each other. So T2, also a 2 meter radius away, and so we'll plug in 2 meters like that. All right, so the net torque should be 0, but it's also equal to T1 times 2 meters minus T2 times 2 meters. Now the 2 meters, I can divide both sides by 2 just to get rid of them, and you realize that tension equals T1 equals tension 2. Now that's totally true in a situation without the guy, but as soon as you add the guy in, the situation gets a little bit more complicated. So let's do this. Here's the scaffold again, and the same net torque equation, because remember, this thing cannot rotate, otherwise this guy dies. So T1, 2 meters, plus Fg, 0, minus T2, 2 meters. Now we add a guy on here that weighs 800 newtons. Okay? He's going to be some distance away from the center of rotation. So we don't know what his distance is. But he weighs 800 newtons. And so I'm going to throw in, let's say he's standing on this side. That's okay, right? I'm not making a rule. Yeah, so let's say he stands on this side, so he's also providing a positive torque to rotate it this way. So positive 800 newtons multiplied by some radius x. Now all of this should still equal 0. Okay? Now, this means that we have 2 T1, this goes to 0, minus 2 T2 plus 800x, and we're solving for x. We want to know how far away he needs to be so that one of the ropes produces a tension of 500 newtons. Okay, so now in this situation, if we just looked at the net force had to equal 0. Okay, which means the two tensions together had to support this 500 weight. We got that the T's should be equal. Both of them should have been equal to 250 newtons. So that way, 250, 250, 500, it all balances out. Now, in this case, that same thing has to be true, but with the 800 added on. So net force, okay, needs to be equal to T1 plus T2 minus the 500 minus the 800. Okay? So 0 is equal to T1 plus T2 minus 500 minus 800. And then I add those over. So 500 minus this is 1300. So both T1 and T2 need to add up to 1300 because they have to support the weight of this beam and the guy on it. Now, if this is true, one of the tensions, okay, is going to be 550, right? One of the tensions has to be 550. So if one of them is 550, 550 minus from the 1300 means the other one has to be bigger. So 1300 minus 550 gives us 750, like that, okay? So if one of the tensions is 750 and the other one's 550, 750 is obviously bigger. That's got to be the one that's closer to the guy. So in this situation where I drew him here, it's actually T2 that's going to be this 750. T1 is going to be 550 times 2 minus 2. Okay? That has to be the rule. And then this will be plus 800 times x. And now, if this all equals 0, we can solve this for x. So this is a very challenging problem combining net force and net torque to get the final answer. So 2 times 550 minus 2 times 750, okay? And so what we get is 400 is equal to 800 times x. 400 divided by 800 gives me 1/2 equals x. So that means, according to our math, 1/2 of a meter is how far away the guy needs to stand from the center. So what are my options? How far would the worker stand from one of the supporting ropes to reduce the tension? Okay, so if this is 1/2 a meter, this remaining distance is 4.5 meters. Okay? But that's not one of the options. So what went wrong? How far would the worker stand from one of the supporting ropes to produce a tension of 550 newtons in that rope? Oh, okay. So I figured out how far he has to stand here. It's 1/2 a meter, 4.5 from this one, but it's actually this rope that has the 550 newtons. So he'd have to stand 5.5 meters away. Oh my God, I'm so dumb. This whole thing is 4 meters. Okay, so final picture. Make it as least confusing as possible. I figured out that he had to stand 0.5 meters away from the end. This whole thing is 4 meters. This rope here has the 550 newtons of tension, meaning that this is 2.5 meters away from that rope. So that's how far he has to stand. That's option C. I should try to cut out all of the confusing, incorrect math. Okay, so a 4 kilogram mass is placed 4 meters, and a 6 kilogram mass is placed here. What is the moment of inertia of the system about the y-axis? So this question wants you to draw an axis. It wants you to set up an x and y system. So starting at 0, going to 1, 2, 3, 4, 1, 2, 3, 4. So there's a mass at position 3 and then at position 4. So here's one of the masses. And then there's a position at 3 and then -4 down here. Okay, if I mark that as -4. They want us to know what is the moment of inertia of the system. Well, you should know the general equation for moment of inertia is mass times radius squared. All right? So we have to add up mass times radius squared for the first one, plus mass times radius squared for the second one. And what is the radius? Well, it's the distance each of these things are from the axis of rotation. So it's the distance away from the y-axis. So therefore, the mass is here 4, and the radius is 3. And it's going to be 3 for each of them. So we got 4 there. The second one is 6 times 3 squared again. So 4 times 9 is 36. 6 times 9 is 54. Adds up to, fantastically, 100 kilogram meters squared. So, again, what went wrong? What is the moment of inertia of the system of masses? 3, 4, 3, negative 4. What is the moment of inertia of this system of masses around the y-axis? Thought for certain it'd be 100. Is this not adding up right? Yeah. Yeah, it adds to 90, not 100. That's just a brain fart. Adds to 90. So it's option B. Oh my god.